Well, we're getting to the end of this unit on linear equations and using slope and rate and slope-intercept form and all of that other sort of stuff. And we're now ready to tie a few things together that we've reviewed in this unit and also that you learned in 7th grade. So the I can statement today is I can represent proportional relationships numerically, graphically, and the word we're going to put right here is algebraically. So we spell it just like we would algebra, and then we put an I-C-A-L-L-Y at the end of it. So algebraically is how we say that word. And then the warm-up question deals with some vocabulary. So what do the words numerically, graphically, and algebraically mean? So numerically, so if you say the word numerically, it sounds a heck of a lot like the word number, and that's exactly what numerically means. Okay, it means we're using numbers to describe things. Okay, whoops, numbers to describe things. And as you might guess, if we're talking about graphically, then we're using graphs. And how about algebraically? I left that one for last. Algebraically would mean that we're using formulas and equations. Really, we're using variables. So I'm going to put the word variables right here. So if we're using variables, then we're going to be using some sort of algebra, and we are going to run into some variables today. Okay. So this is actually the end of the worksheet. We're going to do a couple problems from your assignment today. So if you follow along, you've got a couple problems already done by the end of our discussion here. So proportional relationships that we learned about in 7th grade and the ones that we reviewed at the beginning of this particular unit, they are special cases of linear equations. Now you may remember doing these in 7th grade, but we're going to take a look at these problems that are coming up, and we're going to see if we can identify these connections in the relationship between linear equations and proportional equations and proportional relationships. So here's what we've got. It says the following table shows the purchase data for an item that is sold by the pound. Graph the data and answer the following questions. So we've got some data right here. So we've got pounds in the first column. So this is going to be kind of like the X in this particular problem. And then we've got the total cost. We've got the dollars over here. So this is going to be like the Y. So I'm going to label the X axis over here, and I'm going to put LBS for pounds. And I'm going to label the Y-axis over here. So here's our Y-axis, and I'm going to label this as dollars. So we've got pounds down here, dollars here, and a reminder that of course the horizontal axis is X, and then the vertical axis is the Y. So it says, what is the rate of change? In other words, what's the slope? And it says, be sure to indicate units in your answer. So if we look through here, we've got 0, 0, 1, 3, 2, 6, 3, 9, and so forth. I'm going to go ahead and graph those. So we're going to put a dot right here for 0 pounds and $0. 1, this is 1 pound, and then $3. So $3 would be about right there. It's already scaled for us and everything. 2 pounds would be $6. 3 pounds would be $9, so 9's right there, and then 4 pounds would be $12. $12 a little bit off the charts, but it kind of matches up with the pattern right here. So we're all set there. Now you'll notice that this makes a nice straight line, so I'm going to go ahead and grab this line tool and put a line on here. So we're all set there. Looks like things match up pretty well there. Going to make that a little bit thicker. Okay. So there's our graph. We've got our data, we put our graph out here, and it says what is the rate of change. Now we could calculate the rate of change a couple of ways. So I'm going to calculate it on the table, and I'm going to do it this way. Again, when we've got a table, you can calculate the rate of change using any two pairs that you want. So let's go from this purchase to this purchase right here. So let me highlight those. We're going to go from that purchase to that purchase. So we want the change in the second quantity, so that's going to be the change in Y. So that's going to be 9 minus 6. And again, I'm hoping a lot of this looks familiar, divided by the change in the first quantity, or the change in X in this particular case. So 3 minus 2. So we end up with 3 on the top and 1 on the bottom. So that is 3. Remember, this was dollars and the bottom was pounds. So this is $3 per pound. There's the answer. And I can also get that on the graph. Let's take a look at from this point to this point. These are 2 points that we didn't use over here. So from this point to this point, we're going to go up 3, and then over 1. So this would be 3 and this would be 1. And what I'd like you to notice is that when we're going up, there's actually a label for that. When we're going up, we're counting up the number of dollars. So this is up $3, and this would be over 1 in the horizontal direction. Remember, that's pounds. So this would still be the $3 on the top for the rise and the £1 on the bottom for the run. So either way, it's going to be 3 pounds per dollar. Okay, so we've got our units on there. We're all set to go. And then it says, what is the y-intercept? Well, the y-intercept is 0. Okay, now when we say y-intercept, we don't need to put 0, 0. 0, 0 is the particular point, but when we say y-intercept, all we need is just that one particular value. Where does it cross the y-axis? It crosses the y-axis at 0. Now, if we've got the rate of change, or in other words, the slope, and we've got the y-intercept, then we can write an equation that represents this. So we're going to write y equals, remember it's the slope, it's the rate of change, it's m, that's going to be 3 times x, and then plus the y-intercept. The y-intercept in this case is 0, so it's y equals 3x plus 0, or we're going to clean that up and we're just going to write y equals 3x. There's our answer for this. And we also want to state what x and y represent. When we're doing these problems and we've got lots of different situations and scenarios, different story problems and stuff like that, we want to tell people what x and y represent. So on this particular case, x represents pounds and y represents dollars. So we definitely want to include that in a complete answer when we're doing this algebraically. Notice that we've covered all 3 ideas already. We've got numbers to describe the situation, we've got a graph to describe the situation, and we've got some variables. We've got this little algebraic equation, this linear equation to describe this relationship. Now it says, is this proportional, why or why not? Well, you know from 7th grade and from what we reviewed earlier, we have a straight line and it goes through the origin. So we're going to say yes, and I'm just going to write proportional, and we're going to say it is a straight line, and it goes through the origin. Remember, we're checking for those things when we're talking about a proportional relationship or a graph that's representing a proportional relationship. It's got to be a straight line and it's got to go through the origin. And then it says, write a short story problem that fits the information. Be sure to give an explanation for the meaning of the slope and the y-intercept. Well, I don't know about you, but around our house we like candy, and candy's probably somewhere in the neighborhood of $3 a pound. So let's write this. Candy costs $3 per pound. Okay, and it says be sure to give a meaning for the slope and the y-intercept. Well, right here, this is the slope. When we talk about this rate right here, when we're doing $3 per pound, that right there is the slope, and the y-intercept would be this. 0 pounds costs $0. Let me make that look like $0 there. So $0. Okay, so this right here would be the y-intercept. The slope indicates how steep the line is, or it's the rate, all set there, and then the y-intercept indicates kind of like the starting point, that it starts out at 0, 0. So whenever we have a proportional relationship, it's got to start out at 0, 0, and then it's got to be a straight line from there. Okay, 2 more quick things that we want to notice, and then one more connection with what we've done in the past. So when we're talking about proportional relationships, the rate is the same as the slope of the line, and slope is the same on the entire graph because it's a straight line. So if we were to check the slope from here to here, we could just do this little stair-step pattern. The slope is always going to be exactly the same because what we're doing is we're going up $3 and we're getting another pound of candy, paying $3 more, getting another pound of candy, $3 more, and so forth. And even if we did a really huge triangle right here, like if we went up $9, we'd go over 3 pounds for that. Okay, and the other thing is that the y-intercept is always 0, so that's the part where it goes through the origin. Okay, now I do want to point out one more connection to what we've talked about before. Let's talk about unit rate. So unit rate, remember, is it's always got to have a 1 in the denominator. And when we wrote the slope this way, so when we wrote, so let me write unit rate here, The slope on this one, or the rate of change here, was $3 per pound. And if we wanted to, we could put 1 pound right there. Well, that is the unit rate. And you may remember this from 7th grade. You can actually identify the unit rate on a proportional graph by identifying this point right here. So if you go over to 1 on the x-axis, wherever you are on the y-axis, that is the unit rate. So notice that we're at $3 right there. That is the unit rate. So it's $3 per pound here. Okay, so we're going to continue talking about these types of ideas. This really represents the bulk of things. There are some details that we'll run across in each one of the different problems that we do, but this is what you really want to keep track of. So a linear equation is just, or sorry, a proportional relationship is just a special type of linear equation. We'll notice that because the y-intercept is 0, all we have is the slope. The slope is the same as the rate, and that rate comes from this little stair-step pattern. The slope is always the same to make that straight line. And if you wanted to find the unit rate, we'd look at 1 comma whatever this particular point happens to be. Okay, so I'm going to slide down here and we're going to take a look at the next one. This is problem number 6. Again, we're doing part of your assignment right now. So it says, examine the following table to see how much Mr. Irving pays his babysitter versus how much Mrs. Hendricks pays her babysitter. Graph the data as 2 different lines and label which line is which. So I'm going to make sure that I do this one in red. So I'm going to circle that one in red, and I'm going to do this one in blue. Okay, so we've got a bunch of numeric data here, and you'll notice that the XY plane is not labeled. It is scaled, but it's not labeled. So we've got enough room to do 1 hour, 2 hour, and 3 hours, and so forth. So I'm going to put 1, 2, 3, 4, 5, 6, and we're going to label that as hours. And then in the vertical direction, okay, so remember this is X, and these would be the Y's that we're going to use here. Now we're going to do these one at a time, so I'm going to kind of scribble this out right here. We're not going to worry about that one for the time being. So Mr. Irving, so he pays, let's see, $10 to begin with. So remember this is going to be in dollars right here. Now, we can't do this. We can't go $1, $2, $3, and so forth because we're going to run out of room really quickly. We might be able to fit $10 in here, but we're not going to be able to fit $20 or $40 for sure. So here's what we're going to do. We're going to take this and we're going to go 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. Okay, and we can still kind of see here that's definitely going to be able to fit all of the data on here. So I'm going to continue graphing the numeric information, the data that we have from Mr. Irving. So let's see, this would be 1 and 10. So 1 hour and $10, 2 hours, $20, 3 hours and $30. So we're right here, and this, gosh, this looks pretty good. 4 hours and $40. So we're all set right there. And I'm going to go ahead, and if I follow this stair-step pattern, that puts me down about right here. So that looks pretty good. I'm going to go ahead and put a line in here. Okay, put that line right there. Go up through here. I'm going to make that a little bit fatter so it looks a little bit nicer. And there we go with that one. Now I'm going to change to blue, and we're going to graph Mrs. Hendricks. So she gives $14 for the first hour. So 14 would be about right here. So gosh, she's paying a little bit more right there. Okay. Let's see in the next one, 2 hours, $22. So $22, still making a little bit more. 3 hours, $30. 3 hours, $30. So we're right there. And 4 hours, $38. So again, we're doing this one right here. Maybe I ought to cover this one up. Okay, so 4 hours and $38. So 4 hours, $38 would be just a tad less than this. And I'm going to grab a line making tool. Now, if I follow this, this definitely is not going to cross at the origin. So I'm going to put a dot about right there, and hopefully we can get everything to line up here. So let me go right through there, and I might have to make some adjustments to this. Okay, so I've got this all adjusted. Everything looks good. Now let's go ahead and take a look at the questions here. It says, what is the rate of change for Mr. Irving? So for Mr. Irving, let's go through here and let's figure this out. Now, when we talk about rate, remember, if somebody says rate, you should immediately think slope. When somebody says rate, you should immediately think slope. So what is the rate of change for Mr. Irving? Well, we can do this on the graph. So for Mr. Irving, it would be up here and over here. That would be up from 10 to 20, so that would be up 10 and over 1. So this is going to be $10 per hour. Okay, so there's his slope, and we can also identify that from here. So we could take the difference in those y's and the difference in those x's. So we'd do 20 minus 10 over 2 minus 1. That would be 10 over 1. So that would be the $10 per hour. Let's switch over here because it asks for the rate of change for Mrs. Hendricks. We could do the same thing here. So I would have to go from maybe this line or this point to this point. So we would have to go up and we would have to go over. It's a little bit more difficult on this one because remember, once we graph this, and this didn't land on one of those convenient points, we'd have to see what this is. This is 22 and then we go up to 30. So this would be a rise of $8 and a run of 1 hour. So that's going to be $8 per hour. So that's the rate or the slope on that one. And again, we could double check here. I'll just double check with this one, 38 minus 30. And then I'd do 4 minus 3. So 4 minus 3. That's going to end up with an 8 on the top and a 1 on the bottom. So there's our $8 per hour. And it says, when would it be better to babysit for Mrs. Hendrickson and when would it be better to babysit for Mr. Irving? So remember, Mrs. Hendrickson, she's the blue. So I'm going to stick with the blue color right here. So we're looking at this right here. So if you had these two babysitting jobs, and let me erase these little triangles right here. If you had two babysitting jobs or you had two offers, you can tell who pays more by which line is above the other one. So over here, the blue line is above. So Miss Hendrickson, Hendrickson, gosh, I've got two names here, so we'll just call this Hendricks. Miss Hendricks pays a little bit more at the beginning. So actually that is from, if we followed this down here, at 3 hours they pay exactly the same, but from 0 to 3 hours, Mrs. Hendricks pays more. So from 0 to 3 hours, that would be better. And for Mr. Irving pays less at the beginning, but once we get to 3 hours, he pays the same. And then more than 3 hours, and notice that these lines go on. I mean, maybe they have us work all day or, something like that. So once we get past 3 hours, it would be better to work for Mr. Irving. 3 hours or more, okay? Who pays proportional to the hours, Mr. Irving or Miss Hendricks? So what we're looking for, remember, is it's got to have the same slope, it's got to be a straight line, and it's got to go through the origin. It's got to have a y-intercept of 0. Well, this one definitely goes through the origin, and it's a nice straight line, and that represents Mr. Irving. So Mr. Irving does. And the reason for that is it's a straight line that goes through the origin. And there's nothing wrong with the way Mrs. Hendricks pays. It is a straight line. It's just not a proportional relationship. So on this one, you'll notice on the red one, on Mr. Irving, this point right here, 1, 10, that is the unit rate. Okay, that is how much he pays per hour. It's $10 per 1 hour. Okay, now if we tried to do the same thing on the other one, notice that this doesn't work. This was 14. That's 1, 14. That is not a unit rate on that one. She does not pay $14 an hour. She pays $14 for the first hour, but then she pays $8 every hour after that. Okay, so a little bit of a weird situation, but can you think of why someone might pay their babysitters this way? Well, I can think of one. Maybe Mrs. Hendricks, when she needs a babysitter, she really needs them, and so she's going to pay a little bit more out front to get you there, and then she may be gone a long time, so in the end she pays a little bit less overall. For you, maybe she's the type of babysitter or the type of person that only needs a babysitter for a couple hours, and she's willing to pay a lot more and pay you just for your time getting over there or something like that. Okay, Mr. Irving on the other other hand, he's just like, hey, I'm just going to pay you $10 an hour. It's just a flat rate, and things like that. So these problems are pretty representative of the type of problems that you're going to see on the assignments. So again, work hard, pay attention to the details, see if you can spot that relationship between how we work with linear equations and when we can tell that those linear relationships are proportional.